Let's now do another triple integral. And in this one, I won't actually evaluate the triple integral, but what we'll do is we'll define the triple integral, where we're gonna do something similar that we did in the second video, where we figured out the mass using a density function. But what I want to do in this video is show you how to set the boundaries when the figure is a little bit more complicated. And if we have time, we'll try to do it where we change the order of integration. So let's say I have the surface. Let me just make something up. 2x plus 3z plus y is equal to 6. So let's draw that surface. Looks something like this. This will be my x-axis. It's going to be my z-axis. That's going to be my y-axis. Draw them out. X, y, and z. And I care about the surface in the kind of positive octant, right? Because when we're dealing with three dimensionals, we have, instead of 4 quadrants, we have 8 octants. But we want the octant where all x, y, and z is positive, which is the one I drew here. So let's see. Let me draw some. What is the x-intercept? When y and z are 0, so we're right here, that's the x-intercept. 2x is equal to 6, so x is equal to 3. So 1, 2, 3. So that's the x-intercept. The y-intercept, when x and z are 0, we're on the y-axis, so y will be equal to 6. So we have 1, 2, 3, 4, 5, 6. So y-intercept. And then finally the z-intercept. When x and y are 0, we're along the z-axis. 3z will be equal to 6. So z is equal to 1, 2. So the way let's see. So the figure that I care about will look something like this. It'll be this inclined surface. It will look something like that. And this positive octant. So this is the surface defined by this function. And let's say that I care about the volume. And I'm going to make it a little bit more complicated. We could say, oh, well, that's what's the volume between the surface and the xy plane. But I'm going to make it a little bit more complicated. Let's say the volume above this surface, and the surface z is equal to 2. So essentially, the surface z, so the volume we care about is going to look something like this. Let me see if I can pull off drawing this. So if we go up 2 here, and then we draw the top in a different color. We draw the top in green. So this is along the zy plane, and then the other edge is going to look something like this. Let me make sure I can draw it. This is the hardest part. Go up 2 here, and then this is along the zx plane. And we'd have another line connecting these two. So this green triangle, this is part of the plane z is equal to 2. But what we can do is, what the volume we care about is the volume between this top green plane and this tilted plane defined by 2x plus 3z plus y is equal to 6. So this area in between. Let me see if I can make it a little bit clearer, because the visualization, as I say, is often the hardest part. So we'd have kind of a front wall here, and then the back wall would be this wall back here, and then there'd be another wall here, and then the base of it, the base I'll do in magenta, will be this plane. So the base is that plane. That's the bottom part. Anyway, I don't know if I should have made it that messy, because we're going to have to draw dv's and dvolumes on it. But anyway, let's try our best. So, if we're going to figure out the volume, and actually, since we're doing a triple integral and we want to show that we have to use a triple integral, instead of just doing a volume, let's do the mass of something of variable density. So let's say the density in this volume that we care about, the density function, it's a function of x, y, and z. It can be anything. That's not the point of what I'm trying to teach here, but I'll just define something. Let's say it's x squared, y, z. Our focus here is really just to set up the integrals. So the first thing I like to do is I visualize. What we're going to do is we're going to set up a little cube in the volume under consideration. So if I had let me do it in a bold color so that you can see it. So if I have a cube, maybe I'll do it in brown. It's not as bold, but it's different enough from the other colors. So if I had a little cube here, in the volume under consideration. That's a little cube. You could consider that dV, the volume of that cube. It's kind of a volume differential. And that is equal to dx. No, sorry, this is dy. Let me do this in yellow, or green, even better. So dy, which is this length, dy times dx, dx times dz, right? That's the volume of that little cube. And if we wanted to know the mass of that cube, we would multiply the density function at that point times this dV. So the mass, you could call it dm. The mass differential is going to be equal to that times that. So x squared yz times this. dy, dx, dz. And we normally switch this order around depending on what we're going to integrate with respect to first, so we don't get confused. So let's try to do this. Let's try to set up this integral. So let's do it traditionally. The way the last couple triple integrals we did, we integrated with respect to z first. Right? So let's do that. So we're going to integrate with respect to z first. So we're going to take this cube and we're going to sum them up. We're going to sum up all of the cubes in the z-axis, so going up and down first, right? So if we do that, what is the bottom boundary? What is the bottom boundary? Well, the bottom of, so when you sum up and down, these cubes are going to turn to columns, right? So what is the bottom of the column, the bottom bound? Well, it's the surface. It's the surface defined right here. So if we want that bottom bound defined in terms of z, we just have to solve this in terms of z. So let's subtract. So what do we get? If we want this defined in terms of z, we get 3z is equal to 6 minus 2x minus y, where z is equal to 2 minus 2/3 x minus y over 3. This is the same thing as that, but when we're talking about z, explicitly defining a z, this is how we get it. Just algebraically manipulated. So the bottom boundary, and you visualize it, right? The bottom of these columns, because we're going to go up and down. We're going to add up all the columns in an up and down direction, right? You can imagine summing them. The bottom boundary is going to be this surface. Z is equal to 2 minus 2/3 x minus y over 3. And then what's the upper bound? Well, the top of the column is going to be this green plane. And what did we say that green plane was? Well, z is equal to 2. Z is equal to 2. And that's this plane, this surface right here. Z is equal to 2. And of course, what is the volume of that column? Well, it's going to be the density function, x squared y z, times the volume differential, but we're integrating with respect to z first. So we write dz there. And this, I don't know, let's say we want to integrate with respect to, we want to integrate with respect to x for next. In the last couple of videos, I integrated with respect to y next. But let's do x, just to show you it really doesn't matter. So we're going to integrate with respect to x. So now we have these columns, right? When we integrate with respect to z, we get the volume of each of these columns, where the top boundary is that plane. Let's see if I can draw it decently. The top boundary is that plane. The bottom boundary is this surface. And now we want to integrate with respect to x. So we're going to add up all of the dx's. So what is the bottom boundary for the x's? Well, this surface is defined all the way to x. The volume under question is defined all the way until x is equal to 0. And if you get confused, and it's not that difficult to get confused when you're imagining these three-dimensional things, say, you know what, we've already integrated with respect to z. The two variables I have left are x and y. Let me draw the projection of our volume onto the xy plane. And what does that look like? So I will do that, because that actually does help simplify things. So if we twist it, so if we take this y and flip it out like that, x like that, we'll get it in kind of the traditional way that we learned when we first learned algebra. The xy axis. So this is x, this is y, and this point is what? Or this point, what is that? That's x is equal to 3. So it's 1, 2, 3. That's x is equal to 3. And this point right here is y is equal to 6. So 1, 2, 3, 4, 5, 6. And so in the xy axis, kind of the domain, you could view it that way, it looks something like that. And so one way to think about it is we've figured out if these columns, we've integrated up, down, or along the z-axis, but when you view it looking straight down onto it. You're looking on the xy plane. Each of our columns are going to look like this, where the base of the column, where the column's going to pop out of your screen in the z direction, but the base of each column is going to be dx like that, and then dy up and down, right? So we decided to integrate with respect to x next. So we're going to add up each of those columns in the x direction, in the horizontal direction. So the question was, what is the bottom boundary? What is the lower bound in the x direction? Well, it's x is equal to 0. If there was a line here, then it would be that line, probably as a function of y. Or definitely as a function of y. So our bottom bound here is x is equal to 0. And what's our top bound? I realize I'm already pushing it. Well, our top bound is this relation, but it has to be in terms of x, right? So what is this relation? So you could view it as kind of saying, well, if z is equal to 0, what is this line? What is this line right here? So z is equal to 0. We have 2x plus y is equal to 6. We want the relationship in terms of x. So we get 2x is equal to 6 minus y, or x is equal to 3 minus y over 2. X is equal to 3 minus y over 2. And then finally, we're going to integrate with respect to y. And this is the easy part. So we've integrated up and down to get a column. These are the bases of the column. And so we've integrated in the x direction. Now we just have to go up and down with respect to y, or in the xy plane with respect to y. So what is the y bottom boundary? Well, it's 0. Y is equal to 0. And the top boundary is y is equal to 6. And there you have it. We have set up the integral, and now it's just a matter of chugging through it mechanically. But I've run out of time, and I don't want this video to get rejected, so I'll leave you there. See you in the next video.